Look at a second proportion example. So the National Center of Education Statistics monitors many aspects of elementary and secondary education. In 1996, numbers are often used for a baseline to assess changes. In 1996, 34% of the students, 34% of students were enrolled in free or reduced lunch. In the 2000 survey, the respondents from 8,302 randomly chosen students showed that this figure had slipped to 33%. Do these figures give evidence of a change in student enrollment? Do the hypothesis test confidence interval discuss the type 1, type 2 errors? Okay, so we're looking for a change. So this is clearly a two-tailed test, right? Okay, whoops. There we go. So the proportion of students enrolled in free lunch, and we're doing a two-tailed test. The hypothesis will be a not equal to, essentially. So the question is, do we have enough samples? Are they independent? And is it, normal, essentially? Okay. Well, yes, if you do the 34% times each of these, you're going to get more than 10. So our sample proportion for mean and standard deviation or standard error will obviously be these values here. If we do that, the number is less than 10% of the population, so you can assume independence. It's definitely normal because these are way more than 10 for the and then also they are definitely random, so that's okay. So it's random and independent, so we're good there. Okay, so step 3 would be actually doing it. Okay, so I'm going to do step 3. Okay, so step 3. Okay, so let's go to our thing here. All right, so in the problem, it just said 33%. So we're going to do that. So that means this is, 67, right? So n was 8302. So the standard error is the square root of the 34 times 66 divided by this value here. Because remember, when you do the hypothesis test, this is for the population for the standard error, correct? Versus here, these are the same values here for the confidence interval, except this is the square root of p hat times q hat divided by this. So it's not the same standard error for the confidence interval as it is the hypothesis test. Okay, so the z-stat is obviously the sample minus the population divided by the standard error. Okay, so this is a negative z-value. So we're going to do a normal dot distribution z-value, comma 0, comma 1, comma true, right? And then we actually have to multiply it by 2 to get the actual p-value, right? Because this is a two-tailed test, hypothesis test, right? So let's come on here. Come on. Of course. Okay. So it didn't specify, so we're going to say 0.95 here, which means 0.025 here for alpha, and 0.025 for alpha here, essentially. Okay, so we have a negative z-values, which means it's over on this end, essentially. So the area we're going to get is only half the area, essentially. So if we do the z critical, that's going to be normal, normal dot inverse 0.025 comma 0 comma 1. We get this value here, essentially. Right, so if I draw the picture again, okay, draw the picture. Right, this is going to be 0.95. This will be 0.025. This will be 0.025. Okay, so this is our z star here, or z critical, and this is our z critical here. The only difference is this is plus or minus, right? Plus or minus. So this is the negative one and this is the positive one. They're both 1.95 plus or minus. So our z-stat is 1.92, which means I didn't make it to the shaded region. So my z-stat is right here, okay, which is this value right here, right? And the area of this, just this half, is over here essentially. So I need to double it to get the p-value because I need the area over there also. So 0.027 is half and 0.0544, which would be both of them essentially. Okay? All right. All right, so step 3. Right, so 0.033 was our sample, was what it said, right? So it's now 33%. So we did our z-stat, and we got 1.923. So we did the normal distribution up to there. Wait a minute. That's negative. Negative. We got the wrong value, sorry. Okay. All right, so you double it, you get this essentially. Okay, so what does that actually mean? All right, step 4. Step 4. So if we compare the values, what is the actual case? So copy, paste. So 0.054 is clearly more than 0.05, thus we should not reject the null hypothesis. So our sample proportion is not significant and likely to occur. There is enough evidence to reject the null hypothesis. It is not likely the enrollment in free or reduced lunches has changed since 1996. Okay. All right, so that's our findings. So if we talk about the errors, right, we could be wrong, right? So, and as far as being wrong, okay, alpha is your type 1 error, beta is your type 2 error, right? Either we determined it has changed and it didn't, or we determined it didn't change and it actually did, right? False positive, false negative. All right, let's do the confidence interval, right? So confidence interval. Let's calculate that now. Bold, underline. Okay. So if I calculate the confidence interval, that's going to be z alpha 2 times the margin of error. So what's interesting about this is we're going to have the same alpha, because this is also a two-tailed, because confidence intervals that we do are two-tailed, right? So it's actually the same alpha, right? So we have 0.95. Unlike before, it was a one-tail versus a two-tail, right? So this is now z alpha, divided by 2. The negative one, this is z alpha divided by 2. That's the positive one, right? So confident, your answer is in here, right? All right, so we need to go from here to here, because this is half alpha, correct? Which is 0.025. So from here to here is 0.075. So normal dot inverse 0.975 comma 0 comma 1. There's that. So the z value times the standard error is what we get there, right? So the confidence interval is the sample minus the margin of error, and the sample plus the margin of error. So that is our confidence interval there. Okay. All right. So that means, go back to here, this is our confidence interval. Okay. Make that blue, format, color, blue. All right. So what you notice is our alpha here and our alpha here actually match, because the hypothesis test is 2-tail and the confidence interval is 2-tail. Versus the prior problem, this alpha is 10, this alpha is 0.5, because the confidence interval is a 2-tail and the hypothesis test is only 1-tail, not the same alpha, right? So a lot of times what they'll do is they'll distinguish them by doing like alpha sub h and alpha sub c, right? What you saw previously in my notes for confidence interval, and to distinguish that they're not the same alpha, right? There's two different curves essentially. Okay, did I get the right value? 3.1? Yes, 3.4. Okay, so what do we notice? So the hypothesized value is 0.34, right? Is 0.34 in the interval? Ooh, yes it is. It's just barely in it, isn't it? So 0.34 is just barely in there. So that means we're in agreement here. We did not reject it, right? Which means our sample is a pretty common one inside the interval, which it is. It's in there, just barely in there, but it is in there, right? So since we did not reject the null hypothesis, there is a chance of a type 2 error. It is likely because the p-value is very close to alpha, right? So look here, 0.054, 0.05, very close. Okay. The hypothesis test and the confidence interval are in agreement. Because we did not reject the null hypothesis value of 0.34, and it was in the confidence interval, right? So we're in agreement because 34 is in there, right? But the problem is it's just barely in there, and this p-value and alpha are very close. So there's a high likelihood of a type 2 error, right? Because we did not, we said it didn't change when it might have actually did, but who knows? It's very close. You'll never know, because again, what I'm trying to get to here is as far as type errors, you'll never eliminate them, right? Just changing your alpha value, the significance is going to just change the likelihood of one versus the other. But it is inference, so you're just inferring as to what you believe the outcome is.